Hello, y'all. This is Darrell Lee Berry Jr. We'll be doing some matrix multiplication. What I'll do is go through multiple ways of multiplying matrices, which is part of my exam coming up on tomorrow. So here we go. So basically the idea is, this is for the background. And by the way, this is generally section 2.1 of the book. So if you have a matrix, you'd always have a certain amount of rows, which usually they have denoted by M, and columns N. So A equals A 1 1, A 2 1, A M N, A 1 N, A M 1. So this left column is always the first column. That's why the second column is always 1. This first row is always the first row. That's why the first number is always 1. So here's the row. Here's the column. And let's say we have matrix A, B equals C. So we're going to multiply matrix A by matrix B and get C. And let's say A is 1, 2, 3, 4, 0, 7. And let's say B equals 1, 2, 0, 1, 1, 5, right? Let me make sure I'm in the right part of my notebook here. One moment here. There we go. Notice in my the little dots, excuse me, the dots on my page were not formatted like I wanted it to be. So those are matrices. Now, one detail about matrix multiplication, this is 2 rows, 3 columns, and this is 3 rows, 2 columns. So the inside numbers have to be the same, and then the outside numbers will determine what the matrix will be as a result. So C will be a 2 by 2, since 2 is on the outside of each. So first we'll have matrix multiplication. We'll say dot product way. We can treat the matrices as a group of dot products. So A dot B, well, not dot B, but times B, equals that times that. So we can say that equals, and what I'm going to do is I'm going to dot product each row by each column. So that'll be 1.1 plus 2.0 plus 3.1. And then you'll be going for a 2 by 2 matrix. 4.1 plus 0.0 plus 7 times 1. So that's going to end up being our first column, column 1, and then we'll do this again with the second vector, vertical vector, column vector, dot product with the both of the columns, both of the rows on the left. So that'll end up being 2.1 plus 2.1 plus 3.5. Then it'll be 4.2 plus 0.1 plus 7.5. Let me make sure I didn't miss anything. So that is our column 2. So that will give us 1 plus 0 plus 3, 4 plus 0 plus 7, 2 plus 2 plus 15, 8 plus 0 plus 35. So that will equal 4, 11, 19, 43. And 4, 11, 19, 43 is a 2 by 2, so that is correct. So that's the first method. The second method will be linear combinations. So I'm going to copy this down. We use the same vectors, except this time we'll make linear combinations of column vectors. So this will be 1 times 1, 4, plus 0, 2, 0, plus 1, 3, 7. And then we have 2, 1, 4, plus 1, 2, 0, plus 5, 3, 7. What I did here was take each of the columns of matrix A and let them be the vectors for a linear combination of the columns in vector B turned to the side as if they were rows. So that's going to be 1, 4 plus 0 plus 3, 7. And then we have 2, 8 plus 2, 0 plus 15, 35. So that's going to equal 4, 11, and 1943. And 4, 11, 1943, same thing we got last time. And it's a 2 by 2. So we know from the principle that it is correct, right? So the next way will be a linear combination of rows. So we'll call this one a linear combination of B vectors, of A vectors, linear combination of A vectors. And this one will be a linear combination of B rows. So either linear combination of A vectors or a linear combination of B rows. All right. So linear combination of B rows, you would have 1, 1, 2, plus 2, 0, 1, plus 3, 1, 5, and then we have 4, 1, 2, plus 0, 0, 1, plus 7, 1, 5. So this equals 1, 2, plus 0, 2, plus 3, 15, and 4, 8, plus 0, 0, plus 7, 35. So that's going to then equal 4, 19, 11, 43. And we see that is the same. 4, 19, 11, 43. And then the last way is called compression. Or outer product. Well, basically what we do is pretty much a dot product, but you write it differently. So this would be basically everything is going to be kept in its same orientation, but bundled together. So 1, 4 with 1, 2 plus 2, 0, 0, 1 plus 3, 7, 1, 5. What I did was just take each column of A and outer product it with a row of B, compression, outer product. So that's going to be actually scaled through. So ironically, you put it here and scale it, which I think is weird. I'm going to write these differently. So what we will have is 1, 1, 4, 2, 1, 4 plus 0, 2, 0, 1, 2, 0 plus 1, 3, 3, 7, 5, 3, 7. So that's going to be 1, 4, 2, 8 plus 0, 0, 2, 0 plus 3, 7, 35, 1535, which equals 4, 19, 11, and 43. So that's actually pretty similar to the linear combination method, just there's an extra step in the middle. You end up pretty much doing the same thing. Let me see how it's different. Well, it's actually very different because with that way, the vectors end up side by side right away. But here, the cross ones are mixed up. Whereas here, they're right next to each other. And then you adding an entire matrix together. So it is a bit different. On the vector way, you get a column at a time. And on the compression way, you get the rows at a time. And you add the rows together. So that's 4 ways. I did find a website that promises to perhaps provide additional ways. So and it probably won't even be necessary at this point. This is a MIT site, MIT Linear Algebra. So this is the dot product way, which we did here. That dot product ended up being that one position. Actually, let me make this blue. So we call this the dot product way. Yeah, so this way is saying each column of B times the whole matrix. So the whole column I don't think we did it that way. But we did right here. So take each column and being multiplied by the whole matrix. That's what we did here. This column was multiplied by the whole matrix. And then this column was multiplied by the whole matrix. So we call that the linear combination method. And this became this column here. Right? So the third way that says take each row multiplied by the whole matrix, each row in A multiplied by the whole matrix. So I believe that's this one. Oh, hold up. That one seems ugly. So we did that way. We call that the compression or dot product way, this way here. And this distributes the outer product. Well, technically, this is the, what is it? So I don't know what to call this one. I'll just call it compression. You have to remember that we distribute this. We distribute this to both of these. This third one, though, I didn't see this one yet. A row times a matrix is a row. I don't even know if I want to try that one. And the fifth way says chop it into blocks. All right. So the row by the whole matrix and the inverse, I'll leave that for another time. That's too far from what we're doing in our class. But I suppose it's good to know about. So that's enough for this session right here. I'll save this link real fast so I don't forget. And what I'll do is come back, take a little break, come back and work on uh, another concept or problem or what have you. I'll just keep on going through till I run out of time. So I have several hours. So I'll check back in about 20, 30 minutes and I should be going again.